Hello, good evening, everyone. So, we welcome you to the fifth day of the Science Week. And today we'll be doing something about maths, especially for teachers, right? I hope you all enjoyed and found the previous
Hello.
sessions interesting.
Good evening, everyone. So we welcome you.
And today's speaker will be Dr. Shivkumar M. He is with C2 Sapling Education. He has done his PhD from the Department of Electronics from Indian Institute of Science. And he's also part of this state focus group for the National Curriculum Framework, which is coming up as part of the next step for the NEP 2020. Okay. Shivkumar, over to you. You can start the session.
Okay, Shyam. Thank you for that. So welcome, everyone. So this is the next session as part of the Science Week that we are all celebrating together. Before I continue, Shravan, is my voice audible and is my screen visible? Okay. Right. So let us jump into today's session. Okay. So some quick rules for the participants who have joined from Zoom. So keep your mic on mute if you're not speaking, and if possible, keep your video on so that I can see you. And today, I don't want this to be a one-way monologue. So I want all of you to experience the process of doing math. So please keep pen and paper ready. And if you're attending from mobile, it's good if you keep it as it, you have this wide screen. Okay. And what are we going to do today? So we're going to do some interesting mathematics. And as Shravan mentioned, this is a special edition for math educators and for those who are interested in math teaching in general. Okay, so this is but since we are going to discuss mathematics, I guess it would be interesting for others who are interested in math as well. And the second component of today's discussion would be like how to make classrooms a place of active and joyful learning. So these are the two main discussion points of today. And before going into the session, I want to give you all one right. And that right is right to be wrong. Okay. So immerse yourself in the process. Hope you enjoy it. And feel free in sharing your answer. So in Zoom, you can share it in the chat. And if I ask out, you can turn on your mic and speak out. And we also request the participants who have joined from YouTube to share your responses in YouTube chat. Okay. So we'll start with a quick puzzle, which we call the sock puzzle. Okay. So here is it. Imagine there's a dark room and it has a cupboard. Okay. And that cupboard has 5 pairs of red socks and 5 pairs of black socks. So 10 pieces of red and 10 pieces of black. Okay. Now you need a pair. Okay. So the question is, what is the minimum number of pieces you need to take so that you have a pair having the same color? Okay. So Zoom participants, please send your answer in private chat to me, Shivkumar. Okay. And YouTube participants, please, you can share the answer in the chat. I repeat the question. So you have a cupboard, 10 pieces of red socks and 10 pieces of black socks. Minimum number to be taken out. It's a dark room, so you cannot see the pieces. So you just have to you know how many pieces you're taking. That is all you can guarantee. So what is the minimum you need to get a pair having the same color? Okay, Divya ma'am has given an answer. Okay, I'll just wait for a little more time. Shravan, you can let me know if there are any responses from YouTube. I guess there is a slight delay from here and YouTube. So we'll wait for a few more moments. So Divya ma'am, can we do better than this?
Chinmay has said 6 pieces.
Okay, great. So Divya ma'am has said 11 and Chinmay has said 6 pieces. Okay. So can we do even better than that? Okay, so Divya, can you unmute and say why you feel it to be 11? Or you can put it in chat, whichever is convenient for you. So one initial approach that one would be tempted to take is, exactly. So if all 10 are red, so okay, fine. So Divya's response is, you take out 11, so you take out the first 10 pieces, and if all the first 10 pieces turn out to be red, then the 11th piece would be has to be a black. But then already in the 10 pieces, you already have a pair, right? If it is first 10 red, then already you have a pair. Okay, Vishnu says 2 in YouTube. Okay, so how 2? It could be 1 black and 1 red, right? Then you won't have a pair. Right. So I got a response 3, right? So are you able to see why 3 is the minimum? Because if the first one is a red and the second one is a black, the third one has to be either a black or a red, and you have a pair, right? So this puzzle we found in a very famous puzzle book written by Martin Gardner. He has been collecting puzzles throughout his career of scientific writing, and it has inspired many generations of mathematicians, that puzzle book. So you can search that out after the session if you have not already done so. Okay, so with this quick puzzle, we will go into our exploration time. For that, I will share my whiteboard. Just give me a moment. Right. So is my whiteboard visible to all? Okay. Okay, so I will start with okay. I have written down 2 numbers, 1 and 64. Okay. Now the question is, do these 2 numbers share any common property? What are the common properties shared by these 2 numbers? So from the question itself, it's clear that there need not be one answer. So just go for it. Okay. And here you can put your chat to everyone. You can put your response to everyone. Okay, squares, very nice. Cubes, very nice. So squares and cubes. So that seems to be one property is common to both, right? So this is nothing but 1 square, and this is also equal to 1 cube. And this is equal to 8 square, and this is also equal to 4 cube. Right? So this is one property that is common. So these 2 numbers are both squares and cubes. Okay. So at this point, are any questions coming to your mind?
So Shiv, one more observation is both have a common factor of 1.
Both have a very nice, very nice. Absolutely, yes. Both have a common property of yes. So as I said, these 2 numbers share many common properties. But for now, we will just focus on this property of both of them being a perfect square as well as a perfect cube. Very interesting. Okay. So now question is, okay, so now the thing is, now does this raise any questions in your mind? You can post your response in chat. Take some time. I'll pause for a moment. Any questions?
Soham from YouTube says both are powers of 2.
Both are powers of 2. Exactly. So Jayashree has made another observation. Correct. Are there other such numbers? Right. So are there? One question is, are there other such numbers, or are these 2 unique? Are these 2 only such numbers? Now you can put your answer in private chat for those who are joining from Zoom. Okay. Yeah.
Excuse me, sir.
Who is
Excuse
this?
me, sir.
Ridhima. Ridhima, can you put your answer in chat first and then we'll discuss? Or having a question?
Okay, sir.
Great. So yeah, so first we'll have a period of silence where people work out, and then when we discuss, I'll call out your name first. Okay, yeah. So one question is, are there finitely such numbers or infinitely such numbers, or only these two? Okay, and Nitya has given an answer. Okay, so Nitya, can you? So Nitya has told there are infinite such numbers like this. Very interesting. So again, in private chat, can you say why you feel so? So Ridhima, do you also think that there are infinite such numbers, or these two are the only such exceptions? Okay, Chinmay Bhagat also feels that there are infinite such numbers. So can anyone give a possible reason, or why do you think so? Because there are infinite real numbers. Because there are infinite real numbers, we have infinite numbers that are both squares and cubes. Let me just write this reason. There are, so one reason is there are infinite numbers. There are infinite numbers, and so there are infinite numbers that are both squares and cubes. Is this logical connection? Is the logical connection between these two statements strong enough? Does this lead? Is this a direct logical implication, or is it something that increases the confidence level of this statement? Okay, great. Okay, fine. So there are several class of interesting problems in math where these kind of questions come, right? Can you think of any other question which asks if there are infinite such class of numbers that comes to your mind?
Sir, my chat box is not working.
Okay, Ridhima's chat box is not working. Maybe you can try logging out and logging in again. Okay, right. Another very classical example of this kind of a question is, how many primes are there? Exactly. Jayshree is asking, how many twin primes are there? Right? And 2000, 3000 years back, the Greeks had given a beautiful proof for the fact that there are infinite primes. And that proof till now, so lots of mathematics have come till now, but till now it stands as like one of the most beautiful proofs in mathematics, right? And then of course the next question of twin primes. So the question of twin primes again has its origin in Greek math. How many twin primes exist? People feel that there are infinite twin primes, but till now this question is unresolved. Okay, so how many twin primes are there? How many twin primes exist? Right, so this question is still now, for over 2500 years, this question is still open. Right. Yeah, so what is a twin prime? Exactly. Okay, yeah. So I'll just quickly explain what's a twin prime. So twin primes are primes which are separated by a gap of 2. So basically 3 and 5. This is a separation of 2 and both of them are primes. 5 and 7 separated by a gap of 2 and both primes. 7 and 9 are the twin primes? No, because 9 is not a prime. Okay, 11 and 13 again twin primes. So there seems to be lots of twin primes, right? But as you go higher and higher, the occurrence of twin primes keep reducing, which can be expected. Right now, will this go on forever? What's the question? Okay. Some more responses. I'll just take some time. How can we find the pair of co-prime numbers? Exactly. So yeah, we'll have to leave a number in between, right? So how do you so given a pair, how do you find if they're co-prime or not? So basically, it's a question of what is the meaning of co-prime. If they have common factors, they're not co-prime. If they don't have any common factors, they're co-prime. So one way is by just looking at all the factors of first number and all the factors of second number and seeing if there are any common factors. So this is the basic definition. But then what is the efficient way of doing it is a different discussion altogether. So today I will come back to our original question of finding a number which is both square and cube. Let us come back to our question. Okay. Now, let us take this. Now, since let us take this number 64. 64 is nothing but 4 cube, and this is also equal to 8 square. And then, of course, we have this 1, which is equal to 1 cube and also 1 square. Right? Okay. Fine. Let us take this. Let us take a product of 2 cubes. Let us just take this. Okay. Let us multiply 2 cube numbers. Okay, both of them are cube numbers. What can you say about the product? So this question at now, it seems that this question is like not all related to the first question, but there is a link. So we will start examining this question and then go back to, and we'll see what light this throws on our original question. Okay, so a question is, if I multiply 2 cube numbers, what can I say about its product? You can take some examples. Let us take an example. Let us take 8 is a cube number and 27 is another cube number. The product is 216, right? Fine, we have this 216. Does 216 share any common property with 27 and 8? Actually, 216 is also a cube number, right?
It's a cube of 6.
Yeah, it's a cube of 6, right? So this is nothing but 6 cube. Okay, now let us take a bigger example. Let's take a bigger example. 1331. It is 11 cube. Okay, let us multiply it with another huge cube. Let us multiply with 216. Okay. So would this answer be also be a cube? Can anyone give a
66 cube.
basic explanation of why this should be the case?
11 into 6 whole cube is also there.
11
11 cube into
6.
6 cube.
Right. But why? So how can we be sure that 11 into 6 cube is also the same as 1331 into 216?
11 into 6 cube is equal to 11 into 6 whole cube.
By exponential rules.
Right. So if you have to okay, so one thing is we can take recourse to the laws of exponents. Okay, but if you have to see from where the laws of exponents are coming, right? We can make this beautiful rearrangement. So 1331 is nothing but 11 into 11 into 11, and 216 is 6 into 6 into 6. Now if this is a cube, then I must be able to write this as something into something into something, and all these three must be the same, right? So the question is, how do you distribute these 11s and 6s into 3 baskets so that all the 3 baskets are the same? What can you do? So is it possible to distribute these 3 11s and 3 6s into 3 baskets so that all the baskets contain the same objects? Then it will be a cube, right? Then we have argued that it's a cube. What if I take 1 11 and 1 6 and put it in the first basket? Now, can anyone complete this approach?
11 into 6, 11 into 6, 11 into 6.
Exactly. I can take, so now I can take the next 11 and next 6 and put it in the second basket. And I can take the next 11 and 6 and put it in the third basket. Right? So this is nothing but 11 into 6, the whole cube, the law of exponent that you're mentioning about. Right? So basically this law of exponent follows from this beautiful property of associativity and commutativity of multiplication. Right? So you have a set of numbers to be multiplied. It doesn't matter in what order you multiply them. Okay, and you can also like flip the numbers, but still the product will be the same. Okay, so because of this interesting property of multiplication, we are able to do this. Okay, great. So let us come back. So now it is clear that the product of two cube numbers must also be a cube number. Right. So let us just make down this observation. Product of two cube numbers is also a cube number. Okay. Now, what if both of these cube numbers are the same? Now, if I put the same cube number, okay, I put a same cube number, say C here and C here, then the answer is of course a cube number. But C into C is also a square number, isn't it? So C into C is a square number because it is C square. And product of two cube numbers is also a cube number, which we have seen. Okay, so now I'll pause here again for some time. Okay, so from these observations, now look back into our original question. Can we find a number which is both a perfect square as well as a perfect cube? Does this throw any light?
C square cube and C cube square.
Exactly. Right. So who gave this answer?
Mehzabin.
Oh, great. So now, can you find the next number that has this property after 64? What is the next number? Nitya, yes, you got it. So now, whoever has made this observation, can you share the next number that has this property? So 1 has this property of being both a square and a cube. 64 is the next number. What is the third number? I'll pause here again for some time. So all of you, take your notebooks and start working out, start playing. Let me just write the combination again. So 1 is nothing but 1 squared and 1 cube.
So 27 multiplied
by 27 Ridhima, yes?
29.
Yes, can you repeat again?
So 27 multiplied by 27 is 729.
27 multiplied by 27. What is that? Very nice.
Sir,
So
729.
excellent, Ridhima. Excellent. Very nice. So 729 is 27 squared. And what cube is it?
9 cube.
9 cube.
Exactly.
9 cube.
Yes. So Ridhima, how did you work this out? How did you choose 27 into 27?
Sir, I know the table of 27.
Oh, no. So what made you feel that 27 into 27 would be a perfect cube as well as a perfect square? It's okay, fine, but very nice. And it is surprising that you know the table of 27. Wow. Awesome. And Nitya had raised your hand. You can speak out.
Sir, I also found out another one, which was 4 cube into 4 cube equals to 4096. Sir, 4 cube is 64, and then sir, 60. When we calculate both 4 cubes, we'll get 64. Then that will be 64 square, and then that will be 4096.
Great. And what cube is it?
Sir, it's the cube of 4.
Is it
Four
cube of
cube.
4? 4 cube is 64, right?
Yes, sir.
It is the cube of 16.
Ah, it's a cube
Yes,
of
sir.
16. Very nice, very nice, very nice, very nice. Excellent. Okay, so now for those who have not been able to like make deductions from this observation, just look at these numbers here. Okay, so look at, so this one is 1 squared, 64 is 8 squared, 729 is 27 squared, 4096 is 64 squared. So what is common among these numbers? 1, 8, 27, 64.
Sir,
And
sir,
all
all
the
cube
squares.
numbers, sir.
Squares.
yes, yes, yes. And look at the base of these cubes. 1 cube, 4 cube,
Squares.
9 cube, 16 cube. They are all squares.
They are all squares.
Right?
1, 4,
Yes, sir.
9, 16.
Yeah. So what does the pattern reveal? What must be the next number below?
25.
25 cube and what square?
Sir, it's 125. Sir, no.
Excellent. Excellent. Right. So 25 cube and 125 square, some number, that is the next number having this property. Right. So now we
Yes,
have
sir.
seen a way of generating all such numbers. Right. And there is another characterization of it which Nitya mentioned. Do you want to turn on your mic and specify that, Nitya?
Yes, sir. Laws of exponents, sir. So, let's say there's 4 into 3, like 4 cube into 4 cube. So that will also be, sir, 4 cube in 4 cube whole squared. Okay, sir. So what we'll get here is using the law of exponents, then any a cube whole square, or a to the power of m into the whole power of n. Sir, after that we'll be multiplying those powers, so
Right,
that way
right,
we'll
right.
get in this example we'll get 3 into 2 6, so 4 to the power of 6.
Right. So 6. Right. So the final statement, can I just repeat again?
Sir, 4 to the power of 6 in this example.
4 to the power 6. Right.
Yes.
So this would be 4 to the power 6. Right. And can 729 be written as a power of 6?
So can you just repeat once?
Can 729 be written as a power of 6?
Yes, sir. Yes, sir.
What power of 6 is it?
Sir, power of 3 to the power of 6, because sir.
Excellent.
Yes,
That is
sir.
3 power 6.
Because 9 is square of 3.
Yes. And then what about 64?
Sir,
What
2
power of
to
6?
the
Two.
power of 6.
Very
Yes, sir.
nice. Very nice. This
Sir,
is,
1 to the power of 6.
and this would be?
Sir, 5
Sir,
to the power of 6.
Right. So what is another characterization of all numbers that are both perfect squares and perfect cubes? Can you make another characterization of it?
Sir, their square roots are also, their square roots equal to no, their square roots are consecutive numbers, sir.
Square roots are consecutive numbers. Square roots of these numbers are not consecutive numbers, but I think maybe if you take some time and rephrase the statement, you will see. But for now,
I think
yes,
they are geometric progression.
geometric progression. Which are geometric progression?
So they are the sixth power of natural numbers.
Exactly. So if you see, if you take the sixth power of natural numbers, right?
Yes, sir.
Automatically we're getting this number which is both a power of square as well as a cube. Right? Nice.
Yes, but sorry, I was thinking about some other sequence.
Right.
These are power of 6. Yeah.
Correct. No, yeah. So there is, I mean, whenever we have something, we should like try to look at it at different angles. And there's no.
When I got confused.
No problem. Fine. Okay, so now at this point, are any more questions coming to your mind? Okay, so now we saw that it is not just 1 and 64, but there are infinite such numbers which are both squares and cubes, right? Any further questions coming to your mind now at this point? So we can extend these questions, right? Now, can I find a number which is both a perfect cube as well as perfect fifth power? perfect fifth power and perfect seventh power, right? So numbers that are both fifth power and seventh power. So it should be like 2 power 5, and it should also be equal to some other a power 7, something like this. Is it possible? Right? So this is a whole class of problems, and I would encourage you to just think about it after the session. Okay, but for now we'll just pause with this exploration. Okay, so now we have been talking about cubes and squares. At this point, I just want to share one very interesting number that is related to cubes, and that is very much related to we Indians. Okay, and that number is 1729. Does this ring a bell in any of your head? 1729, what is it?
Ramanujan number.
Exactly. Who was it?
I'm a teacher, Sunita Bhatia.
Fantastic, fantastic. So this number is, as you said, a Ramanujan number.
This is a tax number.
Exactly. It's a
Not
taxi
taxi.
number. Yes. So can you tell something more about this number, about the significance of this number? Why is this number special, and why is this number called Ramanujan number?
There is a cube or square is coming it 1729.
Very close, dear. Very close. Very close.
When he was sick in hospital, some friend visited in that car number.
Yes. So yeah. So he was. There was this great English mathematician named Hardy. So he recognized the genius of Ramanujan, and he took him to England. And there, unfortunately, his health deteriorated. Ramanujan's health deteriorated, and he was in hospital. And Hardy goes to visit him in a car, and he enters the room and says, hospital room, and says, "Today I came in a car which met with an accident, and it has a very unlucky number 1729. There's nothing special about this number." So these both were number theorists also, and whatever number they see, they always like tend to dissect it and look at its properties. Okay, so 1729 was one such number, and Hardy mentions that this is a very insignificant number. But Ramanujan immediately says, no, this is a very special number. So what is the specialty of this number? He says this number can be written as sum of two cubes.
Yes, sir. 10 and 9.
Very good. So 9 cube plus 10 cube. So 9 cube is nothing but 729.
729 plus.
So for those
16
cube is
729.
729.
So this is sum of two cubes, right? So now this is something, anyone who is a little bit interested in math could have said, right? There's no big deal in this. So if you know
16.
If you know all the cubes till 15 or 20, you'll be able to say this, right? But then Ramanujan went one step further and he said, this can be written as sum of two cubes in another way also. So what he said was, 12 cube, incidentally, it happens to be 1728. So now can you tell me what is the other expression?
Sir, one cube. One cube. One square, one cube.
Very good. One
So
cube
1 to the power 0 is coming it 1, sir.
One cube.
So 1 to the power 0. 1 to the power 0.
Yeah, but we are trying to express it as sum of two cubes. Okay, so we are taking it as 1 cube and 12 cube. So even this we can say that, okay, any person who is like little bit involved in maths will be able to say this, right? But Ramanujan did not stop with that. So why this number is so famous is, he said, no other number lesser than 1729 can be written as sum of two cubes in two different ways. So he further says, this is the smallest such number. This is the smallest such number having this property. So there are how many numbers less than 1729? 1728 numbers. So he says from numbers 1 to 1728, no number can be written as sum of two cubes in two different ways. 1729 is the smallest number. Remarkable, right? So it is said that Ramanujan had this kind of an intimate relationship with each and every number. So having this property. So this is why this number is so famous. And even Hardy was amazed seeing the spontaneity of the response. Okay, right. So now at this point, again I'll pause. And yeah, so we're talking about Ramanujan, right? If you look at his origins, very humble origins. He was born in a place near Kumbakonam, and he did not have enough money to buy papers to work his math, and he was struggling financially, but still he was like pouring all out in math because of his love for math. And after some time, he went to Madras University and he presented some of his results to the math professors there, and they could not follow what he was saying. And they said, okay, and they realized that this man had a great potential, and they recommended him to send his work to some England mathematicians. Some of them might see and appreciate and might give him opportunities. So Ramanujan wrote a letter to 3 mathematicians. Okay, 2 of them did not reply, and only one replied, and that was Hardy. So there's an interesting movie made on this. I think it is there in YouTube. You can check this out. So
great mathematicians are Ramanujan.
definitely yes, coming from that background. So it shows that, like, it shows the immense potential of us, of our children, right? So if they're given a proper direction and proper space to grow up, right, then we can do miracles. Okay, so now seeing Ramanujan number, right? Any questions coming to your mind? Any questions or thoughts? Okay, yeah, so some interesting things in chat. So some say that he did not complete high school. Actually, he completed high school, but he did not finish his degree because of his he spent all his time doing mathematics and he neglected other subjects. So I think he did not pass a few of the papers. So because of that, he did not get a degree. That is true. High school he finished, but then after high school he became like too obsessed with it. The Man Who Knew Infinity, exactly, is a movie that I was talking about. Arit, you can share that in to all. Correct. Yeah. So yes,
can I
yes.
say something?
Please.
Yeah. So this is the smallest such number having this property. I have read somewhere that there are more such numbers, 6 more numbers.
Very interesting. Okay. So what's your name?
Nazneen here, Nazneen.
Okay. Are you a teacher?
Yes, a maths teacher.
Excellent. Okay. So now let us look at Nazneen ma'am's statement. So is 1729 the only such number? Again, the same question, right? Is 1729 the only such number? It is the smallest number, as Ramanujan told. Are there more numbers like this greater than 1729? That's the question, right? And Nazneen ma'am says she has read somewhere that there are 6 more such numbers. Okay, fine. Let us explore this question. For now. Now, before going to cubes, right? Let us come one step down and look at Ramanujan numbers of second power. What do you mean by Ramanujan number of second power? Let me just write it. So Ramanujan number.
Sir, is magic square. So magic box.
Correct. Here, this is a lot of work on magic square also. But what I'm talking about here is, of course, all these things which you're saying, right, are definitely wonderful areas of exploration. But due to the lack of time, I'm cutting short on this discussion. But please do continue your explorations after the session ends. Okay, and you can post your responses to us. We would love to hear from you. Okay, so Ramanujan number of second power. Can anyone guess what would be the meaning of this? I'm giving a new name to you all. Okay, Ramanujan number of second power. Can any of you guess what I'm trying to denote?
Sir, from that we can explain any even number by writing it on the power of 2.
Explain any even number as writing as power of 2. Okay, that is one thing. Okay, any other guesses on what I'm trying to mean? Right. So one response here in Zoom. Shravan, any responses in YouTube? Okay, fine. So here we saw that 1729 is the smallest number that can be written as sum of 2 cubes in 2 different ways, right? Can we find a number, smallest number, that can be written as sum of 2 squares in 2 different ways? Right? This is for Ramanujan's level, this was too easy and he didn't even care about it. But shall we take up this problem and using this, we will try to analyze if there are more such Ramanujan numbers beyond 1729. Great. Okay, fine. So now I will pause for some time and I throw the challenge to you. Okay. Can you find a number here which can be written as sum of two squares in two different ways? And no number should be zero. So no zeros here. So no zeros anywhere. Okay, yeah. So I throw this challenge out. Let us see which Ramanujam among you is able to find this. Yes, only natural numbers. Only natural numbers. So no root 2, no irrational numbers, no root 3s and all. Just natural numbers. First of all, is there any such number like that? That is one question. So I'll pause here for a few minutes. Let us see which Ramanujan is going to respond. 1729 can be written as, okay, so Chinmay is saying 1729, can 1729 be written as sum of two squares in two different ways? 41014. Okay, so also, along with the answer, also give how they can be written as sum of two squares in two different ways. And one more thing is we're looking for the smallest such number, right? I give you a hint. This number is less than 100. There's a number within 100 which has this property. Okay, so come on now, go and crack at it. I hope you're all working out. Okay. Sum of two square numbers in two different ways. Gargi, it's a wonderful question. Oh, why not just try? Take a prime number and see if it has this property. Very good thought process. Go ahead.
6 square and 8 square.
Okay, interesting. So Chinmay has one answer. Okay. So take 6 square.
Sir, 6 square is 6 is 36. 8 square is 64. Add it 100. So 10 square is coming.
Great. And what is the other representation for this?
Sir, 9 square or 3 square?
9 square and 3 square. But 9 square and 3 square is giving 90, right?
Sir, it's coming with 100, sir.
Which one? 9 square is 81. What is 3 square? 9.
So it's 9.
Sir, are we talking about Pythagorean triplets?
You tell me, are you talking about Pythagorean triplets?
I think so. Are we
In
close to
Pythagorean
that?
triplets, we have even the left hand side to be a perfect square. We need this also to be a perfect square, right?
Correct.
But here,
So
this number can be anything. Like Ramanujan number is 1728, right? This can be anything. 1729. But these two should be squares, and it should be written as sum of two squares in two different ways.
Okay.
Okay. So I will.
Shiv, there is also a question that can the numbers on the right be the same? That is.
Yes, they can be same. They can be same. Absolutely, yes. Okay. So I will. Okay, I'll reveal the answer, but let me see. Okay, so there is Reeth has given 4104 is 16 cube plus 2 cube and 15 cube plus 9 cube. Great. So, to simplify task, we came to squares. Ramanujan number of second powers. So Reeth is in cubes. Great. But can you find an example for squares? Yes, this number is under. Okay. So Ashwin has put an answer. Let us take this number 50. Okay, 50 is nothing but 1 squared plus 7 squared. This is also equal to 5 squared plus 5 squared. Isn't it? Right. And you can check that this is the smallest such number. I guess this is the smallest such number, if I'm not wrong, having this property. Right? Okay, so now the question which the teacher asked, like, is 1729 the only such number having this property, or there are more numbers beyond 1729 this property, right? Now the same question can be asked for squares also. Is 50 the only number, or are there more numbers beyond 50? Because now squares are little easy to handle, right? Any other example that you can find out having this property?
So 325.
Okay, interesting.
25 can be written as 1 square plus 18 square, right?
Yes, excellent. Yes. Then?
Correct?
Correct. Yeah, and this can be written as 17 squared plus 111.
Sir, 10 square or 5 square is 125, 125.
Okay, great. Another example. So 125 is what? 10 square plus 5 square, and then another example. Okay, great. So 325 is another number. Very nice. Yes. There seems to be another number. Yes. Gargi has given 5 square plus 7 square. Oh, okay. So 325 is also 100 plus 225. Very interesting. Oh, the 325 seems to have triple representation. Okay, fine. So now at this point, let me ask you a pointed question. Okay, we know 50 has its property, right? Take this number 200. Okay, can you just check with 200?
Sir, 100 square and 10 square and 10 square.
10 square and 10. Okay, great. Very nice. So 200 is nothing but 10 squared plus 10 square. What is other representation of it?
So wait for 2 seconds.
What is the closest square to 200?
225, no? 15.
225 is beyond 200. Yes, below 200.
14 square 196.
Exactly. So 14 square plus what square?
14 square plus 2 square.
Exactly.
14 square plus 2 square.
2 square plus 14 square is 200. Right. Yeah, and it was nice that you gave this other examples also. I'm sure if I'd given more time, you would have found more such examples. Okay. But since we are like trying to see if there are more such Ramanujan numbers of degree 3, I'm just hurrying up. So now at this point, I just want you to observe these two cases here. Okay. Do you see any connection between these two? The
Second set the squares of the same.
Can you repeat again? Your voice got lost.
Second set is the sum of the squares of same numbers, like 5 square plus 5 square and 10 square plus 10 square.
Correct.
That should be.
That is one observation. Very nice. So one observation is.
Sir, and the second one is a multiple of the first.
Yes.
1 2s are 2 and
Yes.
7 2s are 14.
7 2s are 14.
Yes. And Arnav, you had raised your hand, please.
Also 5 2s are 10.
Yes. Arnav, you had raised your hand. Do you want to?
But on LHS, it becoming 4 times of the number.
Correct. So basically, you just look at this, this 1 here and this 2 here, and this 7 here and this 14 here, and this 5 and 10 and 10. So basically, all are like double, right? They're just doubled. And what has happened here? This has become 4 times.
4 times.
Okay, so now are you able to guess what will be the next number in this line?
800.
800. Wow.
4 square plus 28 square and 20 square plus 20 square.
Just a moment. So 800 would be what?
4 square plus 28 square.
Okay.
And 20 square plus 20 square.
Okay, so can you actually verify this is true? 28
Yes.
square is 700 64 32 38 yeah, 784, right? And 784 plus 16 is indeed 800, and 20 square plus 20 square, right? So this is
Yes.
nothing but 784 plus 16. 784 plus 16 is 800, and it's clear that 20 square plus 20 square is 800, right? So now let us come to this question. How many is the sum of two squares in two different ways? What do you think?
Can you repeat?
Can you repeat?
How many such numbers exist?
Infinite.
So how many?
Infinite.
Infinite, right? No,
As
again,
we can multiply it many times.
right. So now why is this happening? Why, if we are multiplying, if we are doubling each of the base, this property is holding? Can anyone give an explanation for that? Can anyone give an explanation of that? So let me just write it like this. So 50. Yes.
Sir, so there is a number x and that is squared plus y square in the first line if we see.
Correct.
So if we times it to 2x whole square and then 2y whole square, then we take
just a moment. This little more story so I can write what you're saying. So you have a number x. And
yes, and we
equal
square
to,
it.
You square it.
No, sir, the number is n. N is equal to x square plus y square.
Okay.
Now if you take 2x square plus 2y square.
Okay.
Now we take the 2 common. So 2 in bracket x square plus y square.
Okay.
So now because x square plus y square was n.
Yes.
Okay, I did some mistake there. I
No
think
problem. No problem.
2, 4. So that 4n would come. So
exactly. So this would be. Just a moment.
4.
Very nice. So what's your name?
Arnav.
Arnav. From which class are you in? Arnav? Arnav, which class are you in?
Ninth.
Very nice. Right?
Yes, sir.
So the second number is 4 times n1. Right? So again, a simple property of exponent and commutative and the distributive law of multiplication. Right? Fine. So then instead of 2, if we can multiply with 3, would that work? What is so special
Yes,
to
sir.
is one
Then
question.
n2 will be 9 times n1.
Okay, yeah, wait. So I'll just again leave this question open for you to explore. Okay, so now the aim of this is to like show different explorations for you, which you can take up and work after the session. Okay, so don't leave it, Arna. Very nice. Excuse me. Okay, so now with this observation in our hand, right? Let us come back to the question which one teacher raised. So Ramanujan number I have 1729 equal to 9 cube plus 10 cube and 1 cube plus 12 cube, right? Now, are there more such numbers? How many such numbers? Can you generate one more number having this property? Anyone?
Yes,
Sir, what?
So what I'm asking is, now we have seen this Ramanujan number here, right?
Yes, sir.
It can be written as sum of 2 cubes in 2 different ways. Now, can you find another number that can be written as sum of 2 cubes in 2 different ways? So can
100.
Just multiply those x and y's into 2. So it will be 18 cube plus 20 cube.
Very nice. Very nice. So find another number can be written as sum of 2 cubes. Sum of 2 cubes in 2 different ways. Okay, right. So just if you multiply by 2, then what should you multiply the LHS with? So I take this 9 and multiply with 2. So basically I have 18 cube plus 20 cube and the next becomes 2 cube plus 24 cube. What will happen to 1729? What will that be multiplied with?
8.
Exactly. Right. So this is another number having this property. Right. So now how many such numbers are there now?
Sir, 16 cube or
Sir, the number is 13,832.
13,000. Okay. 13,832. Okay. So now we have another number having this property. So now a teacher had mentioned that there are 6 numbers of this form, right? Ma'am, now what do you think about that statement? I forgot your name, sorry.
Nazneen.
Nazneen, yes. So yeah, so now what do you think about the number of numbers having this property? Do you think they are just limited to 6?
No, they can be more.
More, right? So how much? 50? 100?
Infinite?
Exactly, infinite, yes. Right, so there are infinite numbers having this property, in fact. Right, and we just saw that just using this property of, again, a law of exponent and the distributive property of multiplication, they are in a position to generate infinite such numbers. Okay, and 1729 happens to be the smallest number. And what more, for squares, right, it is more easy to get a complete characterization of these numbers. So numbers that can be written as sum of 2 squares in 2 different ways, right? There is a way of systematically getting all these numbers since they are squares. So if you are familiar with algebra, right? So basically, it's like trying to come up with a number n, which is a square plus b square, and also c square plus d square. Right?
Yes.
So now if you,
Sir,
if you
a
just,
square plus 2ab plus b square is equal to c square plus cd 2cd plus d square.
but dear, here it is not a plus b the whole square. This is not, but this is a square plus b square. Just a square plus b square.
Yes, sir. Yes, a minus b plus a minus b or a plus b.
Okay. Just after the session, just look at it to see if a plus b the whole square is actually equal to a square plus b square. You can just substitute different values for a and b. Okay, take a equal to b, 5 equal to 3, and just check if they're equal or not. Okay, great.
So, is there some method or just it is just trial and error?
No, there is a systematic method which you can get from this. Okay, if you want, I'll just give the next step. So this would be nothing but basically we're looking for a, b, c, d having this property a square minus c square is equal to d square minus b square.
Yes, sir.
Right. So now with this, both of this has a beautiful factorization. Right. Now how can we exploit this factorization to come up with this numbers here? Okay, you can work on this after the session. Right. Okay, fine. So now we have been talking about basically laws of exponents. We saw how these laws of exponents got unraveled in 2 interesting problems, isn't it? When you're talking about exponents and numbers, right? Let us just start with the numbers. We started with the numbers 1, 2, 3, 4, 5. Okay. Any idea in which country did this way of writing numbers originate? So in which country? Did
Greece.
This, just a minute, this way of writing numbers originate? I'll give you 4 options. Okay, I'll give you 4 options like kaun banega crorepati. One is, okay, we'll go with Greece. B is England. C is India. D is an Arab country.
Sir, D.
Greece.
Okay, Greece. So I can see Greece and I can see Arab country. Okay. Anyone else wants to take any other guess?
Greece.
Greece, Arab or Greece, Greece. And I see one India. Who gave it? Okay, there's lots of messages here.
Shivkumar, maybe you should give the 50-50 option and remove 2 options.
Okay, 50-50 option. Okay, since okay, fine. So since Shravan is asking for 50-50, I am removing these 2 countries, Greece and Arab country, out. of the picture.
Sorry, South sir, Greece and
Can be
Arab countries.
India from Arab country.
Sir, India. Sir, it's India.
India.
It is India, right? Along with zero, right? Along with zero, this system originated in India. Okay, and then this system.
Sir, use it, sir. Zero, which country?
India, correct?
Sir.
Right. So please mute yourself, those who are not speaking. Okay. Sean, can you mute?
Sir, zero's Roman number.
Okay. So now this, yeah, okay. So this originated in India.
Yeah.
Okay. And then during this medieval period, right, 12th century, 13th century, many great Arab scholars came to India, and they went to different places. They also came to India, and from here they picked up the system and introduced to Europe. Okay, until that time Europeans were using the Roman system. So for Roman system, you have to invent new symbols for new numbers, right? So 10 would get an X, 50 would have is it L? Then 100 would be a C or a M. Then 500 would be some M. So as you keep increasing the number, sorry, what is it? D. So in Roman numbers, you're like forced to come up with new symbols, right?
Sir, 1000 is M.
Okay, darling, this will do for now. Okay, but
if someone is asking what was zero in Roman numbers?
The thing is, Romans did not have zero. Okay, Romans did not have zero. Okay, other civilizations did have a number system, which is very close to what we are using. Like the Babylonians had, the Chinese had, the Mayans also had, right? But the current system has its origin in the Indian system, and it was Indians who first gave zero, who treated zero the same way we treat other numbers. Okay, so other civilizations also had this little glimpses of zero, but it was Indians who gave the same treatment for zero as numbers. They said you can treat zero as any other number, and they're not just stop here. Brahmagupta went to negative numbers. Again, this was the first Indian contribution, and he also treated those negative numbers at par with other numbers, and he gave all the operations that we use now, right? That it has its first origin in the works of Brahmagupta, right? So Indians have made a lot of contributions to math, and of course, with this being a few of them, to know more of India's contributions, I would ask you to refer to you a talk by Manjul Bhargava, which he gave just a few days back. Okay, I think it will be available in YouTube. Just search for it. So there he lists down 10 contributions, which is even relevant for school mathematics. Okay, and zero and negative numbers are few of them. Okay.
Madhur Bhargava, you said, sir?
Yes, Manjul Bhargava. I'll just write his name.
I'll share the link of the video in the end of the session. So towards the end of the session, I'll share the link.
Thanks, Tom. Thanks for that.
Thanks
for that. Okay.
Shiv, yeah, sorry to interrupt. I just check the time and yeah.
Sure. Right. Fine. So yeah, so since there is this time thing, we'll just end with this last one activity. Okay, yeah. So now we have this system of writing numbers, right? Let me just ask you one question. Just take a quick guess at this question. Okay. Suppose you start counting numbers from now. Okay, for another 100 years. So let us just take this hypothetical scenario. So you start counting numbers. Okay, one number every second. You count so fast. One number every second. Okay, and you count for 100 years without stop. 100 years without sleeping, taking rest, nothing, just counting numbers. Okay, what number would you have reached in the end? I know this can be exactly calculated, but just give your estimation of how many digits would the final number be. So what would be the
11?
What would be the number you reach?
Sir, 3,100,000,000.
No, this looks like have you used calculator to
600,000.
calculate it, or do you already know this?
Sir, 600 billion.
Sir,
Oh my God, you people already you calculated this or what?
Sir, you
Sir, maybe 1000 digits.
Okay, 1000 digits. Okay, 1000 digits. 1000 digits is one answer. Okay, because you're counting for a lifetime. So when people say lifetime's work, right? This is literally a lifetime's work. You're not doing anything else and just counting. Okay. So what number you would reach and how many digits it would have? Any other guesses? Quick guesses. Okay. The actual answer, if you actually do the calculation, right? It's not such a difficult math to do. It comes somewhere around this number.
yes, sir. I calculated.
Yeah, I
Yes,
just
sir.
I asked you to predict first before calculating. Okay, anyway. So this is the number. So just look at the number of digits it has. This just has 10 digits.
Sir, 10 digits.
I just want you to hold back and just see. You count throughout your life, and the number you reach in the end is just a 10-digit number. Just imagine how much time it will take for you to reach 1000 digits. Would your lifetime be enough for that? So of course, lifetime is
Sir, it will take thousands of years.
Thousands of years is an understatement. So just think about it a little more. Okay. Yeah. So with this, I will end the explorations today. I will get back to my slides. Okay. Just give me a moment.
Sir, it's 100 years. This answer is 315 into 10 is coming. Sir.
Okay. Yeah. So for now, because of shortage of time, I'll just cut short this discussion. So now,
Okay,
so see now again, this shows the power of the way of writing numbers, the place value system. So just using 10 digits, right, we're able to represent such an enormous number, right? Okay, now just visualize these big numbers. Okay, Earth's age is estimated to be 4.5 billion years. Okay, just imagine how many lifetimes you need to live to see through the entire Earth from the beginning till now. Just think about it. And the number of people on Earth is 7.75 billion. So we can count only till 3 billion at this speed, right? So just imagine if you have a super bike, okay, and your objective is to see all the human faces. Do you think it will be possible in your lifetime to see all the human faces? Just think about it. And this number can be just written in such a succinct, compact way, right? And look at this, the number of cells in the human body, right? This is 3.72 into 10 power 13, right? Remember,
Sir, that's about 3 trillion.
right. But just remember the fact that at the beginning, we are just a single cellular zygote. Okay, we are just a single cell zygote. And for a single cell zygote to divide into so many cells, right? Just imagine how the division should have occurred to reach this number. We just saw that if you just keep adding 1 every second, even if you add it every second, right, you won't reach this number. Okay, now then, so to reach this number, how should the division be? Just think about this. Okay, Avogadro number, I think you some of you at least might be familiar with this. Right? It's a number of atoms in a mole. So basically, if you look at carbon 12, and if you just take 12 grams of carbon, it has approximately 16 to 10 power 23, not 9, 10 power 23 atoms. So just imagine if you are an atom, right? How big a world is, how big an universe is this 12 grams of carbon. Okay, and the last is the most mind-boggling of all. The total number of possible chess games, right? It is estimated to be at least 10 power 120. Okay, 10 power 120 is, again, you can just try to make an estimation of how many years it will take to just see through all the games. Okay, fine. So now we'll just have a quick reflection time. This is especially for people who are interested in math education. Okay. So now we're coming to the second component of our session, right? So what can be done to make math classrooms a joyful and an active place of learning? Okay, please put your answers in chat. I will pause for a few minutes for you to give your response.
Sir, I have a question.
Please.
You were also using the word perfect square, right?
Yes.
How can you define that the square is perfect or imperfect? What is the logic in using the word perfect square?
what is the logic in using the
Word,
are you asking what is the meaning of perfect square, or are you asking what is the justification of, I mean, is it right to use the word perfect there? Is that your
both.
question?
I'm asking both.
Okay, so perfect square is a number which is nothing but product of two same numbers. So 3 into 3, 4 into 4, 5 into 5, 6 into 6. These are all perfect squares. This is the name we are giving to those kind of numbers. Right.
Is
So
it
now,
right? Because only when you multiply a number with the same number itself, then only in that case you will get a number which is called as a square number.
Correct.
So if we are using the or what? How can I say? If you are using the word perfect square, then isn't it a kind of repetitive word?
Yeah, fine. Yeah, that is up
We
to.
don't have to.
Yeah. Yes, correct. You don't have to. Yes, it is just a convention. Yes.
It is a convention.
Sure.
Yeah. Okay.
Right. Okay. Yeah. So now the question is, what can be done to make classrooms a place of active and joyful learning? So please put your answers in chat. YouTube people, please put your answers in the response. Okay, let me just go through the responses. So using animations is okay. That is one thing. Math games. Make them interactive with out-of-the-box questions, activities. Okay. Activity-based teaching. Okay. Nazneen ma'am, would you consider today's session as an activity-based teaching?
Absolutely, sir.
Right.
Absolutely, because
right. So
everybody was involved and thinking. It was a mix of everything, sir. We were out of the box thinking was there, involvement, interest, everything.
Right. So one thing is activity-based.
I basically dramatize also a little bit. I dramatize a lot of things while teaching. So that also adds interest.
Absolutely yes. Very nicely, very important thing. So which classes you teach, ma'am? Which classes you teach?
Sorry?
Which classes do you teach?
I teach 7th to 10th.
Very nice. And this element which Nazneen ma'am saying, like being an actor, dramatizing things, definitely it is very important. It has a very great impact on students. Very nice. True.
So the concepts get very clear because they remember, I myself copy my professor from my college, and now I'm giving it to my students, the drama element.
Very nice. Drama element. Yes. Right. So one thing is activity-based teaching, right? Need not always involve materials, because in math, right, you have these numbers themselves as concrete objects with which you can play. Right. So that is one thing. Yes. Sri Yadav has mentioned create hands-on experience, diversify, make math personal. Math teachers are okay. Joyful activities. Okay. Quiz in maths. I hope just the teachers are responding and not the students. Okay. Learners participation. Yes. Modern technology. Okay. Involve students by questioning method. Okay. Yeah. This is something which I'm going to come to. There's no set rule. Only things is to understand the mindset of the learners and provide what they need. Okay. Lead to outcomes. Collection of photographs of great mathematicians. Absolutely yes. The personal touch has its charm. The history of any subject has its charm when you're teaching. Okay. Problem solving. Absolutely yes. That's a very integral part of the session. Yes. Okay. Sean, anything from YouTube that you want to share, or I can continue?
Math facts or jokes is.
Math facts. Yeah. Right. Exactly. Yes. Jokes are very important again. Okay. Fine. So now, I would want to take your attention to two things. Just two things. Okay. So all the things that you said are very important. So questioning or giving this exploration opportunity, right? Did this make the activity more engaging and involving? Question number one. Okay. So just imagine that if I had just given all the properties beforehand, okay, if I had given all the properties beforehand, and if I just asked you to check it, would the experience have been the same? Keep this question in mind. So the first question is like giving this opportunity to explore, right? Did it make the session more engaging? Question number one. Question number two, giving time to think, contribute in this. So I could have just raised the question and I could immediately given the answer, right? So all the sixth powers are numbers which are both squares and cubes. You can find infinite such Ramanujan numbers by just multiplying. Could have given rules, right? But did giving time enrich this process? Second question. Okay. So now let us just give a name. Let us name the duration in which a teacher gives students questions or explorations, okay, and then gives them time to think, explore, and even make mistakes before they're corrected and answered. Let us give this time a name called exploration time. So exploration time is basically a time where teacher is giving students some challenge or an activity, an exploration, and giving them some time, okay, for thinking, exploring, and making mistakes. Right. So exploration time, if you see, right, this forms a important, the first and probably the most important step in making the classroom a place of active learning. Okay. And because of, so there are various constraints when you are implementing this in the classroom, right? One is the time constraint, which people always say, teachers obviously, and which is true actually. But one good thing is NEP is like asking for reduction in the syllabus precisely for this reason, so that teachers can spend more time exploring concepts. Okay, so that problem hopefully will be solved in some time. But even then, even if this exploration time is implemented partly, okay, not in all the classes, but like once a week, 10 minutes of exploration time a week, right? You can play a big role in enhancing students' thinking and analytical skills, and help students in concept building. So all you have to do is just raise the question and give them some time to think and explore before giving the answer. Okay. Yeah. So what's the time? 30 minutes more. So at this point, I just want to share this quote of George Polya. So please take a look at it. So I'll read it now for you. A great discovery solves a great problem, but there is a grain of discovery in the solution of any problem. Your problem may be modest, but if it challenges your curiosity and brings into play your inventive faculties, and if you solve it by your own means, you may experience the tension and enjoy the triumph of discovery. Such experiences at a susceptible age may create a taste for mental work and leave their imprint on mind and character for a lifetime. So this is an observation made by George Polya, a mathematician. Okay. So now, where can we get these explorations? So if this is a good idea, if you feel, where can we get it, right? So two obvious answers are like generate them ourselves, which is a challenging task, which gets perfected only with time. Second thing is we can use some external resources. So what kind of external resources can we use? One that is closest in our hand, the textbook. So especially these NCERT books have these boxes, try these, do these, enrichment activities, kind of things, right? Usually now, because of this pressure to finish the syllabus, we may tend to skip over those things. But it's exactly these kind of things that has a great potential in making the students connect to the particular topic. So they have a value. And some exercise problems also could be used for this, and mathematical properties also. Yeah. So what these are, we'll see. And we have this web, of course, and there is this website called arvindguptatoys.com. Okay, and you can take. So this has plenty of ebooks which can be freely downloadable. Not only in English, it also has in Hindi and other languages also. You can take a look at this. And there is this nice online textbook called mathtagon.org, which you can check out. And there's also a magazine at right angles. Yeah, so you can just note down some of these resources. There are plenty more. Okay, you can start from a textbook. Okay. And the most important thing is, as we have been saying, so this science week will not end just with this week. This is just the beginning, in fact. So what do we mean by that? So we are offering a course of 12 sessions, okay, which will contain more math explorations, and we would have more discussions on classroom implementation to make it joyful and active or to be done. So now we just saw this idea of exploration time, right, where we give an exploration and give students some time to think. Now, how do we build on this? How do we use these different resources to identify explorations, and how do you proceed in achieving our learning outcomes using this method? Right, these are some questions which we would like discuss in this course. So if you're excited about math and think that exploration time is a good idea to be taken into your classrooms, then this course is for you. So this course is intended for all math educators working at school levels, and also for all math enthusiasts who are not yet into teaching but who would like to take a plunge into it. So both of you are welcome for this.
So there is also a science version of this. So it is both for science and maths teachers.
Yes. So the science version was covered 2 days back by my colleagues. And this course is certified and funded by the academic trust. So because of this funding, this course would be available free of cost to the participants, thanks to the academic trust. And this will be conducted after school hours so that it doesn't clash with your school timings. Further details will be sent soon in the WhatsApp groups. Okay. And who is conducting this course? So we members of C2 Sapling Education, in association with the Academic Trust and Indian Academy of Sciences, we are conducting this. So we are basically graduates from institutes like IISc Bangalore and NUS Singapore, who are very excited and passionate about science and math education. And we have been working with school teachers in making them experience the joy of scientific and mathematical thinking and taking these things to the classroom. So we have been working with school teachers and would like to share our insights with those of you who are interested. Okay, so summary of this today's session was we did some interesting explorations around exponents, and there are still several questions open for you to explore. And then we presented the idea of exploration time. Okay, yeah. So there is one more announcement that we would like to make. Sean, okay, I'll share it. Just give me a moment. I'm just fixing up the system. There are multiple screens to be toggled about. Just yeah. So our Science Week thing is not over yet. So 5th March, that is tomorrow, we have another session, overview of particle physics, another very interesting branch of physics. So as you keep breaking things into smaller and smaller things, what will happen? So from the heart of the matter to the edge of the universe is given by Professor Rohini Godbole from IISc. And then this Sunday we have exclusive student special. So today we had some discussions on classroom implementation also, but we have a special session for students. Magic of math through paper folding, to be taken by Dr. Ashwin Guha from C2 Sapling Education. So these are the upcoming events. And we also have this unique contest. This contest is Quest Fest. So where if you have made any interesting observations or if you have some interesting questions, you can share that with us. Okay, so it's not just the answers, but the questions and observations that you have. It could be about some interesting phenomenon in nature, or some interesting number patterns, interesting geometric patterns, whatever it be, or some interesting observations in the evolution of an organism or a system, anything it be. Or you can share this. So more details about this will be shared later. Yeah, so these are the announcement that I had to make. Fine. So now we have 5 more minutes. I would be happy to take some questions if you have any. So, okay, so yeah. So if you have to get further details about this course, please register. Shravan, the registration details, can you share it? Yeah, he'll share the details in Zoom chat as well.
Already registered for the Science Week, then you will be sent the relevant communication later. If not, I'll share the link where you can register.
Sir, on behalf of everybody, I would like to thank you so much. I mean, it was so interesting. Though I've been teaching for so many years. I think decades, must be 29 years. But the session was really very interesting, and I'm going to carry it forward to my students definitely.
Excellent.
Thank you
Excellent.
so much.
That is what we wanted. Thank you, ma'am. Your name?
Nazi.
Your name?
Nazi.
Nazi.
Yeah,
Okay,
Nazi.
so okay. Which school?
I'm from Dr. Kalmadi Shamrao High School, Pune.
Pune. Okay. Nice.
Pune,
I'm very happy to hear this.
Kalmadi High School. Yeah.
Okay.
We are a very good group of teachers, very interesting staff, and we would love to connect with you.
Great. We'll be also happy.
Yes, sir.
To do that. Yeah. Anything else that you'd like to share or ask? Yeah, so as we saw, there are like a few more questions. Is it possible to characterize all the numbers that can be written as sum of two squares in two different ways? And some of the students were interested. So we could see, right, the students have so much of potential. Like, so there are many Ramanujans lying in our classroom. Just what is needed is giving them a space, little bit of space to use their creativity. If we're just able to do that, then we'll be amazed.
And so if we leave the children with a reflective question at the end of our lesson every day, उनको एक reflective question देके अगर छोड़ दिया, so they get into that thinking mode all the time.
Excellent idea. Absolutely yes.
And I have been using ACID, a question a day, ACID questions.
Okay.
ACID exam, I am sure you are aware of.
Lightly aware of, yes.
Yes, those are very, very challenging questions.
Very nice.
ACID, ASSEST, ACID question. Yeah.
Okay. Nice. Yes. So what Nazim ma'am said is like, again, a nice idea. So can you also use the space outside the classroom to make students think mathematically and scientifically? Absolutely yes. That's a good idea. One thing is, if you also do it in the classrooms, then students who have this fear of mathematics, right? And when we give this opportunity to them and we give them the freedom to make mistakes and play around, then there's higher chance that these kind of students also get drawn into this. So that is one advantage when you do it in the classroom. But then, as Najrin ma'am said, we can also use the time and space outside the classroom for this kind of activities. Definitely is very good idea. And the idea of dramatization definitely is. Definitely, it will make the class very lively. Absolutely is. Yeah. So those who are not registered for the Science Week, please do so. You'll get further information about our courses, and we have upcoming 2 sessions, tomorrow and after tomorrow. Right. So Shravan, anything else that you would like to say?
No. Yeah.
Okay. Yeah. So thanks for your feedback. I'm glad that you liked it. And as Nazdin said, if you take it to your classrooms, then that will make me more happy.
Yeah.
That's a promise, sir. Don't worry.
Wow. Amazing. Nice to hear.
Aslin, ma'am, we would like to hear your experience also. Like, if you're taking it to the classroom, then you can always write to us and say how it went. So
yes, sir. Definitely, I'll do that.
Thank you.
And a request for all the teachers: the aim of doing the Science Week is to spread the joy of doing science and maths. So you can share about this event with your teachers or like with your with your students and fellow teachers from your school as well as from other schools as well. So yeah, please do that. Thank you.
Okay. Thank you.